My name is Glenn Lockwood, and I'm a storage architect at the National Energy Research Scientific Computing Center at Lawrence Berkeley National Lab. It's my pleasure today to present some preliminary work we've been doing at NERSC towards understanding how all-flash storage enables new dimensions of I/O performance. As I said, I work at NERSC, which is the mission computing facility for the U.S. Department of Energy's Office of Science. We serve a broad range of science domains, and in recent years we've been seeing an increasing number of workloads that go beyond traditional simulation and modeling. For example, we've been providing an increasing number of computing and storage resources for the next generation of experimental and observational facilities, which include telescopes, synchrotrons, and particle detectors located around the world. In addition, we're also picking up a growing number of workflows that incorporate AI, both training and inference steps, to aid in the analysis of these new experimental data sources and new extreme scale simulations that can generate petabytes of data per job. As a result of these changes to the HPC landscape, we're also seeing the I/O demands of our workloads shifting, and it's becoming increasingly clear to us that their needs aren't accurately represented by I/O performance analysis based only on simple checkpoint restart benchmarks. Fortunately, flash storage is offering a lot more versatility in I/O performance, and we're seeing several commercial all-flash parallel file systems coming to market specifically aimed at addressing the I/O demands of these new workloads arising from AI and other analytics. And so for the past year, we've been evaluating several of these new all-flash storage systems, and I'll be talking about some of the techniques we've used and the quirks we've discovered along the way. In this study, we used an all-flash parallel file system developed by a company called VAST Data, and this is an overview of our test environment. We used 8 clients connected to VAST via EDR InfiniBand, and our VAST file system encapsulated in blue here included 8 client-facing C nodes and 2 back-end D nodes connected by a back-end 100 gigabit Ethernet NVMe fabric. And our system was spec'd to deliver 40 gigabytes per second of read bandwidth, 5 gigabytes a second of write bandwidth, 168,000 write IOPS, and twice as many read IOPS. The 8 C nodes are where all of the intelligence of the file system are implemented, and they are the hosts that provide the file system out to our 8 clients. These C nodes are completely stateless, and they're all functionally equivalent to each other with no sense of data locality. On the other side of the backend NVMe fabric are D nodes, which hold all of the file system state, but are otherwise completely dumb. They don't do much beyond act as a host to which the SSDs are attached, and they project these NVMe drives to the 100 gigabit Ethernet NVMe fabric using the NVMe over Fabrics protocol. The 2 D nodes are failover pairs for each other, and collectively they serve 12 Optane storage class memory drives and 44 QLC flash drives. I'll refer to the storage class memory drives as either Optane or 3D Crosspoint drives for brevity, but it's worth noting that these findings could apply to any storage class memory technology like XL-Flash or ZNAND. VAST combines both Optane and QLC in a single namespace using a pretty sophisticated data path. When a client issues a write, it goes to any one of the C nodes. The write is then synchronously replicated to 2 Optane drives, and that write is bucketed based on a locality-sensitive hash, so that similar data is logically grouped together. It's also worth pointing out that VAST exposes its namespace to clients using standard NFS mounted either via TCP or RDMA. Since C nodes are locality unaware, there's no need for any fancy protocols like PNFS to get high parallel performance. Instead, the client effectively sprays RPCs across all C nodes using NFS's multipathing capability, and the stateless nature of C nodes makes this synchronous part of the write path very simple. As more writes come in, these buckets eventually fill up into large multi-gigabyte stripes. Once a stripe is full, a C node reads its contents off of the Optane drives and compresses and erasure codes the stripe. Then that stripe is written across the QLC drives, and its contents are expunged from the Optane drives. It's important to note here that the Optane is not a cache, because data either lives on the Optane or the QLC, but it's effectively never on both at the same time. Incidentally, this write buffering on Optane is conceptually similar to how part of the Deos write path works. And so although we're talking about VAST here, some of the results I share may also apply to similar hybrid Optane QLC architectures like Deos. The notable difference with VAST is that it never lets user data be synchronously written to QLC, so write performance is always dictated by the Optane layer. Now that we understand the important bits of VAST data path, the first thing we typically do when evaluating a new file system is to see how much bandwidth it can deliver. As I said, we at NERSC are not exclusively interested in the huge bandwidth hero numbers typically associated with large parallel file systems because we have many applications that run at lower concurrency, use small I/O sizes, and perhaps use limited parallelism when performing I/O. So when we measure bandwidth, we measure a wide range of conditions to quantify how versatile a storage system is for different I/O sizes at different levels of concurrency. We do this using standard methods for measuring bandwidth using IOR. First, we write a bunch of data to many files in parallel to measure write bandwidth, and then second, we immediately read back all of those files, taking care to avoid reading out of page caches. However, to capture the versatility of the file system, we run these IOR tests using 4 different client counts, which we'll call N, 5 different numbers of MPI processes per node, which we'll call P, and 6 different I/O sizes, which we'll call T. Furthermore, for each combination of clients, processes per client, and I/O size, we run each write and read test 5 times. This resulted in 1,200 individual IOR bandwidth tests. We then roll up all of the bandwidth measures for all of these tests and plot them as a function of total MPI concurrency, that is, N times P, to see the average bandwidth deliverable by the file system across many different flavors of I/O for a fixed concurrency. So for example, when we plot the read and write bandwidth for 32 MPI processes, we're really showing the mean across 3 different ratios of clients to processes per node and 6 different I/O sizes each. Upon running this battery of tests, we found that with this all-flash file system, it's delivering bandwidth extremely reliably, regardless of whether we're doing I/O from a few fat nodes with many processes per node, or a lot of thin nodes with just a few processes per node. As long as the MPI concurrency remains the same, we see that the coefficient of variation is very low. This is remarkable when you consider that each one of these bars averages a bunch of bandwidth tests that use very tiny I/O sizes and very large I/O sizes. We also see that read bandwidth scales very well, averaging over 25 gigabytes per second at the maximum concurrency we tested, and we don't see any obvious saturation, which suggests that we are client limited in our test platform. This bodes well for read-intensive data analysis workloads. However, the write bandwidth saturates very quickly at only 5 gigabytes per second. This is not too surprising since every write is replicated and effectively uses twice as much bandwidth as reads. And we also only have 12 Optane drives to service these incoming writes compared to 56 total drives that can service reads. That said, we feel that this write to read imbalance could be mitigated if one uses twice as many Optane drives with half the capacity to improve the peak write capability of the file system. As we were examining the read bandwidth I just showed, though, we realized that those numbers were below expectation, and a lot of our QLC drives were actually sitting idle during those bandwidth tests. If you recall how VAST migrates data between Optane and QLC, you'll realize that the QLC layer in aggregate has much higher bandwidth than the Optane layer, yet data only makes it to this high bandwidth QLC layer if it sticks around long enough to be turned into a full multi-gigabyte stripe. As a result, reading fresh data limits you to the performance of the Optane layer, while reading old data can get over 4 times more read bandwidth from the QLC layer. And as I'll show shortly, data that's somewhere between old and new gets performance that's somewhere in between. So instead of testing read bandwidth by reading data we had just written, we explored what would happen if we read aged data that had been pushed down to QLC. We could test this by first writing data as we did for the naive bandwidth test, but then performing a second write step by writing a bunch of junk data to cause the Optane write buffer to overflow and push all of our originally written data from step 1 down to the QLC. After flushing the Optane, we would then reread our data from step 1 and be able to measure the read bandwidth of this high bandwidth QLC layer. When we do this and read artificially aged data, we see a significant improvement in read bandwidth because on these hybrid Optane QLC systems, data gets faster as it gets older. For example, we saw over 50% improvement in read bandwidth at modest scales by artificially aging our data before reading it to get the full bandwidth of our QLC drives. Now, it's fair to question whether real user data would likely come from QLC or Optane in production environments, and so to answer this question, we looked at our production workload data and found that at NERSC, we expect to see about 6% of our file system's total capacity to be written to our scratch tiers every day. given that VAST uses only 0.5% of its capacity for write buffering, some simple arithmetic demonstrates that the NERSC workload would write 0.5% of its capacity and therefore overrun the write buffers on a hypothetical VAST storage system every 2 hours. Therefore, as long as a user was reading data that was written more than 2 hours ago, it would qualify as being aged. Also, as an interesting aside, another VAST-specific quirk we discovered here is that the stripe compression that occurs when data is migrated from Optane to QLC caused our huge IOR files to compress down to tiny stripes that only landed on a few QLC drives, and therefore only got a few drives worth of read bandwidth. To address this, we had to implement a new random bit pattern in IOR to ensure that our read datasets didn't compress and would be striped across all of the drives. Historically, bandwidth was the one true measurement of performance of parallel file systems for HPC, but the advent of all-flash makes IOPS an equally interesting way to gauge file system performance. Measuring IOPS at the file level is not something HPC has historically done, but there is a standard approach developed during the early days of burst buffers, which involves reading or writing 4K IOs at random offsets to a bunch of files to see how many such random IO operations could be completed every second. As with our bandwidth tests, though, we tested this at many different concurrencies and ratios of clients to processes per node to see how reliably the file system can deliver the IOPS we observe. When we run this battery of IOPS benchmarks, we see that, like bandwidth, IOPS are generally insensitive to whether you're using one node with many threads or many nodes with one thread. However, read IOPS appear to require a lot of MPI processes to drive them, and we see no sign of performance saturation. Conversely, write IOPS show a very high peak performance, but also relatively wide variation, which is in sharp contrast with our read IOPS results. As it turns out, measuring write IOPS using this standard approach was not actually measuring IOPS at all, but instead measuring our NFS client's ability to reorder and coalesce random writes in page cache and gain a lot of apparent performance through write-back caching. Now, whenever write-back cache affects benchmark results, the first thing most people try is to turn on autodirect and bypass page cache entirely. When we did that, we saw a dramatic change in the write IOPS scaling, and it goes back to appearing to behave just like read IOPS did. Low variation and no sign of reaching a saturation with our 8 clients. However, which one of these two results represents the true IOPS capability of the file system? Applications rarely perform truly random writes during scientific computation, and even rarer are the cases when an application that does randomly write does so with autodirect on purpose. So we posit that if you want to measure IOPS to get an approximation of a real application's performance, you're better off leaving write-back caching enabled since most scientific applications will benefit from it. However, if you're trying to measure the peak write IOPS capability of the backend storage system, it is fair to use autodirect to approximate a larger number of compute nodes all running their own IO patterns independently. Of course, this gets even more complicated when you consider the effect of hybrid Optane+QLC architectures. For example, consider an AI training workflow where data is being sent to a supercomputer from an external source, whether it be a telescope or a beamline or any other experimental data source, or a capacity storage tier or even a tape archive. That data would be immediately written to the flash tier as efficiently as possible using large sequential writes, but then it would be immediately read back randomly as the training step of the workflow batched up the input data for training. The benchmarking challenge that arises in this case comes from the fact that large training data sets are likely to overflow the Optane write buffer to some extent. For example, VAST reserves approximately 3 terabytes of Optane for every 600 or so terabytes of QLC for landing new writes. This happens to be roughly the same size as some important machine learning data sets used in scientific computing. For example, we have 2 AI applications at NERSC called CosmoFlow and DeepCam, which incidentally are part of the new MLPerf HPC benchmarks, that have training data sets that are 5 terabytes and 9 terabytes large respectively. Copying one such dataset into a modestly sized VAST file system would result in the earliest parts of the dataset being migrated down to QLC, while the latter parts of it still remain on Optane. We've already established that age data gets higher sequential read performance as a result of this, But the reverse is true for random reads because Optane is exceptionally efficient at delivering high IOPS compared to QLC. So there's two factors at play that affect how we measure the read IOPS of these workflows. One, large data sets can be partially migrated to QLC before being read back during training. And two, QLC has lower read IOPS than Optane. These two considerations mean that the actual read IOPS you can achieve on a dataset is a function of the size of that dataset on these hybrid Optane+QLC storage systems. In the results shown here, we see that a small training dataset, one that would fit entirely on Optane, could get 3 times more read IOPS than an aged dataset that had been fully migrated to the QLC layer. As the dataset gets larger relative to the Optane buffer size plotted along the x-axis here, its read IOPS drop as more of the dataset is striped down to QLC. Now you could make the read IOPS of such a training dataset more predictable if the storage system provides access to data locality controls to allow you to, say, pin the data in Optane to get those higher IOPS. And if any of you are going to implement your own hybrid QLC Optane system, this might be a very valuable feature for your power users. But at the end of the day, predicting how many IOPS your training workload can get out of a hybrid Optane QLC storage system is a lot more complicated than just reading values off a spec sheet. These evaluation efforts are still underway at NERSC, but these findings I've just described indicate that we can't just benchmark sophisticated all-flash storage systems using the same methods we developed for comparatively primitive hard drive-based parallel file systems. When measuring bandwidth, ensure that you're evaluating your storage system's ability to deliver performance at many different concurrencies and I/O sizes to gauge how suitable it will be for both traditional checkpoint restart and emerging AI workloads. When measuring IOPS, don't try to attribute one true IOPS value to a storage system because it will almost definitely be meaningless in most contexts. Instead, be mindful of why you're trying to measure IOPS. Is it to understand a particular application's performance, or are you trying to measure the aggregate capability of the storage system if it's being beaten up by many users at once? For hybrid Optane+QLC systems, remember that reading new data can be misleading. Freshly written data has lower sequential read performance but higher random read performance, and the opposite is true of old data. And to take a step back, what we've really found throughout this study is that the old platitude of you should always benchmark I/O using real application patterns is getting harder to avoid as storage systems get more complicated. We've shown here that not only do I/O patterns matter, but the overall workflow and the timing between different types of I/O can have dramatic effects on the actual I/O performance your workflows experience due to how hybrid Optane+QLC systems migrate data between their different media types. Finally, I'd like to thank our sponsors at the Department of Energy, the field engineering and R&D teams at Vast Data, and you all for your attention.